Hello everybody, I am Ali Nejat. I'm going to cover very important chapter of boundary layer. Boundary layer. Okay, imagine there is a body, for example, a flat plate. In an external flow, the flow is coming in x direction, u infinity. What happens is, in the vicinity of the flat plate, the flow will be influenced by the presence of the flat plate. Right here, due to the familiar standard no-slip condition, there is no velocity. Then velocity is increasing gradually to u infinity. And if I follow that, there is a region in the vicinity of the flat place where the presence of the flat place is evident. This region is called boundary layer, or let's call it hydraulic boundary layer. In this region, the velocity profile evolves. Right after that, the velocity profile doesn't change. So that's the region where velocity profile experiences its change in its shape. As you can see, the thickness of this boundary layer, which is called boundary layer thickness, and it is denoted by delta, is a function of x. This is x direction. Therefore, it's good to define Reynolds number based on the local value. Reynolds x, the local Reynolds number, is defined as rho u infinity x over mu. X can vary from 0 to L. L is the length of the flat plate. What happens? What happens is this. With increasing x, Reynolds number will increase. Therefore, the flow is originally laminar. Then the regime of the flow changes from laminar to the transitional, and then finally turbulent. So in this case, if Reynolds number is less than a critical value, the flow is laminar. If Reynolds number is greater than or exceed this value, the flow becomes turbulent. We have two different scenarios based on the value of the Reynolds number, local Reynolds number. What the critical value is depends on the geometry. For example, for this flat plate, which is a good example, the value is measured as 10 to the power 6. And let me emphasize that delta is a function of x, which is called boundary layer thickness. It's part of the solution. We need to find delta at each section. So what happens is, when the flow becomes turbulent, for example here, we still have velocity evolution, and then here it's flat. Okay, now let's continue with another applied example, this time flow over a cylinder. It's a still external flow, so the flow is not inside the cylinder, it's around the cylinder, u infinity. What happens is this. If the flow is laminar, you can see that the streamlines can adjust themselves with the shape of cylinder. This case. But if I increase Reynolds number, so Reynolds number is increasing. In this case, what happens is, when the flow is getting close to the cylinder, then suddenly it separates and it detaches from the surface. Here, there is one region where some wakes, which is called secondary flow, some wakes appear. And therefore, we call it separation and wakes. This wake reduces the drag. We will talk about that. So, unlike the flat plate, which had a very simple geometry, we will see more challenges when we change the geometry to the cylinder. So, what we need to find for any object subjected to free stream velocity is, first of all, delta as a function of x, boundary layer thickness. This is what I have already mentioned. The other one is this. I'm looking for the shear stress on the surface, tau W. W stands for wall. To make it non-dimensionalized, I can say tau W divided by 1/2 rho u infinity squared. Remember, tau is shear. Shear has the unit of pressure. So I can manipulate it just to tau wall rho u infinity squared. It is named CF, which is a skin friction factor. And just to remind you, when there is a body, for example, the wing of the airplane, airfoil, in the air, the interaction between the air and the body, the solid body, are two forces. One, parallel to the flow, which is called drag, wants to push or drag the airfoil or wing, and the other one is lift, which wants to keep it aloft, the wing. So I'm looking for this drag force, but it's better to repeat the same procedure and non-dimensionalize that. So drag can be non-dimensionalized by the same denominator, 1/2 rho u infinity squared. But remember, this is the pressure, so I need to multiply it by area to convert it into the force. Therefore, I can say that 2d divided by rho u infinity squared a. We call it CD, drag coefficient. So what we are going to do is, in this case, we are going to find this one, CF and CD, for each scenario, each geometry. And please remember that for each scenario we have two different flow regimes, laminar or turbulent. So in the next slide, I will show you how we can simplify the original boundary layer equations and how those equations lead to some correlations for delta, CF, and CD. Okay, let's please continue with simplifying the boundary layer equations. First of all, there are some assumptions that we can apply to the original equations, boundary layer assumptions. The first assumption is this. U, which is the x component of velocity, is much greater than v, which is the y component of velocity inside the boundary layer region. And second of all, changes in y direction is more significant than the change along the boundary layer in x direction. So if we apply those equations into the original equations, finally we will have these equations. This is called familiar continuity equation. The continuity equation remains intact, but the x momentum changes. Okay, one term for the x is vanished, and one important thing, the pressure gradient now appears as differentiation rather than partial differentiation. And also y momentum leads to this equation, which says that p is not a function of y. And on the other word, p on the surface can be assumed from p on the boundary layer edge. It's a good achievement. Let's explain what they are. First of all, this is for a steady state. All these equations are written for a steady state. The point is this: the y momentum equation is reduced to this fact that the pressure doesn't change in vertical direction. Therefore, I can find the pressure on the boundary layer edge and then directly transfer it to this point on the surface. So, and also just pressure changes in x direction. So this term is the only unknown for the pressure in these equations. I know these equations look a little maybe difficult, but the good news is we are not going to go over these equations. All we need is the results of this equation. So what we will do is this. We will solve, these equations are solved for different geometries. In this class, we focus on the most famous one, which is called flow over flat plate. It is called Blasius flow. It is named after Blasius, the German scientist, in 1908. So we will solve this Blasius problem, which is flow over flat plate, for two different cases, both laminar and turbulent. And for each of which I will derive delta CF CD. So we have 6 equations, 3 for each of these cases. These equations, these relationships are derived after solving this big set of equations. And after solving that, I can estimate, okay, when there is a flow over the flat plate, what the boundary layer edge is at each given x, at each given distance from the leading edge. This is called leading edge. Also, I can find shear stress at each point and the total shear stress and the total shear force from CF. Also, I can find the drag at each point and the average one on the surface. Okay. In the next segment, I will provide you those equations and I will solve you some examples.